Hello and welcome to our demonstration on blockchain-based optimal auctions using deep learning. Imagine we have a resource and we want to sell it, but there are more than one buyer who wants the resource. How can we decide which buyer to sell this resource to? Traditionally, the auction is an efficient tool to allocate the scarce resource to the winning bidder. In the process, the scarce resource is also priced efficiently and goes to the bidder that values it most. One of the most common types is the sealed bid auction, in which all bidders simultaneously submit sealed bids to the auctioneer so that no bidder knows how much the other auction participants have bid. This impedes malicious bidding. In this demonstration, we will consider the forward and reverse sealed bid auction. Forward auctions involve a single seller and multiple buyer. For example, like spectrum auctions. In contrast, reverse auctions involve a single buyer and multiple sellers. For example, the government may require a public facility to be constructed. To find the lowest price service provider, the government can conduct a reverse auction. However, in conventional sealed bid auctions, there are some challenges that can impede the price discovery and allocation mechanism of the auction. Firstly, a malicious bidder who does not intend to win the auction can participate in bidding and then evade payment after the auction ends. As such, the common practice is to hire a trusted auctioneer to facilitate the auction to ensure the winning bidder pays. However, the cost of engaging a trusted auctioneer can be expensive. Secondly, a sealed bid auction lacks transparency. A corrupt auctioneer might be bribed by one of the bidders to manipulate the auction results. For example, in government tenders, a corrupt government staff in charge of a reverse auction may allow a bidder to secretly change his bids so that the bidder can win the auction and earn the rights to sell a service to the government. Thirdly, an auction has to be a truthful mechanism. Specifically, the auction design should be such that bidders have the incentive to bid, rather than lie about, their actual valuation. The second price auction has commonly been used to ensure incentive compatibility or truthfulness among the bidders. However, the second price auction might not be ideal since the seller's revenue is not maximized. If we think about it, do we really need an auctioneer? Since auctioneers are expensive to hire and may be potentially malicious, how can we carry out the auction without a centralized authority? Decentralized applications and blockchain comes to the rescue. Next, how can we ensure that bidders will always bid truthfully while also ensuring that the revenue of the seller is maximized? We will use the optimal second price auction using deep learning proposed by Zhaonian in this demonstration. Smart contract contains states of auctions and bids, as well as logic required to operate as an auctioneer. User interaction with the contract is stored in transaction block on blockchain, which is transparent and non-manipulatable. Bidders can place bids through blockchain providers like a browser integrated with MetaMask. Contract deployment can be quite manual at first, and we might want to add in additional data for auctions that do not reside on blockchain, hence we will add in a web server to help with that. In our application we support both forward and reverse auctions. Now we will demonstrate the forward auction process that follows this system architecture. In this demonstration, we will use two browsers, one for the seller and one for the three bidders, and both browsers will connect through MetaMask. Also, a local blockchain is used where there are 10 wallet addresses having balance of 100 Ethereum. Firstly, we will go through the contract deployment phase. We will first use seller account to access the secret endpoint mentioned previously and key in the seller wallet address. After submitting, the contract will be deployed to blockchain. Next, we will create an instance of forward auction using the seller account. Let's say the seller is auctioning second-hand digital assets, and allow 3 bidders to bid for these assets. All the details keyed in will be sent directly to the auction contract for creating a new auction instance in the blockchain, with only the images stored in the web server. After successfully creating the auction, we can see that it now appears in the listing page. If we click on the listing, we can go into the auction detail page to check the related information about the items being auctioned. Now let's switch to the bidder accounts to place some bids. Each bidder needs to input a bid value, deposit and passcode. The deposit value is the Ethereum amount the bidder has to send in together with the bid, and it is required to be higher than the bid value. This is because we want to make sure the bidder will not evade from paying the auction if he becomes the winner eventually, and it has to be higher than the bid because we do not want bidders to know what the rest has bid. The passcode is used to hash the bid value so that no one can see in the transaction block how much the bidder has bid. Hence, in the bidding stage, the contract only keeps track of the hashed bid and deposit amount sent by the bidder. We will use the first bidder account to input a bid value of 2, deposit of 3, and passcode of 111. For the second bidder, we will send in a bid value of 3, deposit of 4 and passcode of 222. For the last bidder, we will send in a bid value of 4, deposit of 5 and passcode 333. When all bidders complete the bidding, the validation stage will start. This stage is required because we only have the hashed bid in our contract, hence we require bidders to send in the real bid value and the passcode to validate his previous bid. Now we will key in the bid values and passcode we have entered during the bidding phase for each bidder. Now that we get all the validated bids in the blockchain, how can we solve the problem of maximizing the revenue for sellers and ensuring incentive compatibility among the bidders? We have added the neural network training in the server. The web server exposes an endpoint for the seller to call for initializing the training. When the server receives the request, it fetches all the validated bids from the contract and sends the bids to train in TensorFlow. After getting the result, the server will interact with the contract again to send in the result for settling the auction. We use the MySonNet proposed by Dutting to determine the winner and payment of the auction. MySonNet is a deep learning-based auction mechanism. In the forward auction, MySonNet helps to maximize the revenue of the seller while ensuring the incentive compatibility and truthfulness of the bidders. Our system first collects the bids from the bidders. Then, the bids are monotonically transformed by a two-layer feed-forward neural network. Using the softmax function, the highest transformed bid is selected as the winner. Finally, we calculate the actual payment of the winner by applying the inverse transformation function on the price determined by the second price auction payment rule. Using the negative value of the revenue as the loss function, we train the network to maximize the revenue of the seller. In the reverse auction, the lowest transformed bid is selected as the winner and we use the payment rule of the second price reverse auction. The network is trained to minimize the cost of the buyer in the reverse auction. This is the complete architecture of the application after adding in the neural network. Next, we will show the final step of the auction. Using seller account, we are able to see that we can trigger the deep learning operations to retrieve the pricing of the item and the allocation result. In the browser, the seller will send a HTTP request with the auction index and type to the web server, and the server will find the corresponding validated bids from the contract and then go through the deep learning process. After the result is out, the server will interact with the contract to end the auction with a winner and final payment price for the auctioned item. When auction ends, the winner's deposit will be deducted by the amount of the final pay price and the rest is refunded. Bidders who lost will have the full deposit refunded. Now we can see the auction detail updated, and the pay price is actually higher than the second highest price, which is consistent with the properties of the MySonNet proposed by Dutting. Looking at the wallet balance, we can also see that the seller, which is the first address, actually gets the amount of the pay price. The winner's wallet also gets deducted by the amount of the pay price. We now evaluate the revenue maximizing properties of the auction. It is shown that for auctions conducted over the blockchain, we are able to achieve similar properties of the MySonNet proposed by Dutting. The winning price is higher than that of the second price auction, but lower than that of the highest bid, thereby preserving the properties of incentive compatibility while ensuring revenue maximization for the seller. Furthermore, we are able to achieve a convergence of the result in relatively few iterations. Next, since all auctions will be carried out on the blockchain and there is a gas fee to be paid for each transaction, it is necessary to perform evaluation on the gas fee for different number of bidders to verify the scalability of the application. In our experiment, it is shown that the gas fee increases linearly with number of bids. This is true for both the forward and reverse auction. For example, it costs only about $50 to hold an auction for 50 bidders.